Hello and welcome. This is a presentation of our paper entitled Uncertainty Prediction for Deep Sequential Regression Using Meta Models. This is a joint work with my colleagues at IBM Research, Matt Arnold and Ben Elder. I'd like to start with a very brief summary of the work. We are focusing here on regression task and uncertainty quantification in such a task. Uncertainty quantification in regression means that we will be talking about predicting lower and upper bound, signifying uncertainty around a regression target being predicted. In particular, we will focus on sequential regression tasks in deep neural networks. And we will be presenting a concept called meta modeling, which I will explain and develop it into a joint meta model, which is a novel part of this paper. We will also present results on a couple of relatively complex sequential tasks that demonstrate the power of the proposed technique. Okay, let me start with a brief introduction into the concept. Overall, uncertainty quantification can be categorized into two classes, roughly speaking, intrinsic and extrinsic approaches. The class of intrinsic approaches consists of methods with an idea that the uncertainty quantification comes from within the model itself as a byproduct of its architecture and parameters. The class contains the famous Bayesian models, for example, Gaussian processes models, ensembles, and various variants of those such as dropout techniques. An extrinsic approach, on the other hand, involves the notion of a base model and a meta model. The base model takes care of the task at hand, which could be classification, regression, ranking, etc. Now, the meta model acts as an observer of the base model while it's performing its task. It gets to see the inputs as well as the outputs of the base model, and it's trained to predict the success and failure of the base model at its task. In a special setting that we call white box setting, the meta model also gets to see the inner workings of the base system with neural networks. This would be the neuron activations, for example. Metamodeling comes with numerous benefits. The list is shown here is not exhaustive. I just wanted to pick a couple of the most important ones. First of all, the concept is very practical. In practice, we often are given base models that come without uncertainty quantification, and we might not necessarily have even ownership of such models or access, or we might not even know their structure. Metamodeling is one very simple way to equip such models with uncertainty quantification. It is easy to include out-of-domain data or model error pattern behavior with meta models, predicting behavior of base models when faced with data that is drifted or in some ways mismatched from their training conditions. And finally, metamodeling has been shown to be very effective. It is at least as good as state-of-the-art competitive baselines, and in many cases can be shown to outperform these. Now, this is a classic deep sequential architecture referred to as sequence to sequence. It consists of an encoder and a decoder. The role of the encoder is to sequentially process an input sequence, to compress it, and to pass such a compressed representation to the decoder. Now, the decoder, which is a second set of recurrent neural network units in this case, then unrolls in time, so to speak, and generates sequential predictions. Parameters of this network are trained so as to minimize the loss function over training data. Now, this would be our base model, as shown here. Now, in the meta model configuration, we cascade a meta model shown on top that has a sequential architecture as well. In general, it can draw on the input and output information, that would be the black box setting, as well as the hidden states, that would be the white box setting. The meta model is trained to predict the regression error of the base model. In our study, we designed the connection shown in this image. The input is on the left-hand side of the encoder is distilled by a fully connected neural network. And the meta-decoder is then fed with the base predictions and the internal states as the base recurrent neural network unit unrolls in time. In our work, we considered a black box setting, a white box setting, as well as a novel joint model in which both of these components, the base and the meta model, are trained jointly. The field of uncertainty quantification is long-standing, and there is correspondingly numerous baselines to evaluate in connection with a proposed method. So we have chosen deep ensembles as one of the baselines, then a implicit heteroscedastic variance, which replaces the output neurons with a Gaussian function whereby the mean is the predicted regression target and the parameter sigma is dependent on input features and generates the uncertainty at that particular point. We have variational dropout for RNNs, which induces random deactivations of connections within the RNN network, and has been shown to be an approximation of the Bayesian neural network. And finally, a more classical baseline from the statistics field termed GARCH. And we also evaluated a constant band reference, which basically amounts to generating a lower and upper bound that are at a constant distance from the predicted target y hat. We evaluated the methods on 2 data sets and 2 sequential regression tasks. The first one is predicting traffic volume. The inputs here are weather conditions on a particular day. The outputs is traffic volume, which is the number of cars registered per hour. The second data set is a physics-based simulation of an oil reservoir output. The inputs here are complex well placements and geology features, and the outputs are predicting or are observations of oil, gas, and water outputs per unit of time, in this case, 3 months over a period of 30 years. Our main metric of comparison is a relative gain of each method with respect to a very simple reference, namely the constant band spanned around the predicted target, as I explained. This means the lower and upper bound are a constant distance away from y hat. And what exactly this distance is determined using calibration data. Now, overall, the metric of gain, large positive gains are good. Zero gain indicates that a method is not better than a simple constant band reference, which may or may not be good, and negative gains are bad. The paper has a lot of experimental detail for different settings. One summary table here shows gains of each method across different data sets. That's the columns and conditions, also columns. And for different rows, which are the proposed models as well as their baselines. The system JMS refers to the joint, the WBS to the white box meta model, which do attain overall highest gains across the board. And I want to refer anyone interested to check the full paper for full experimental detail. Let us take a look at a few samples from the actual data. In these images, the blue dashed lines are regression predictions. The orange solid lines are actual observations. So that's the ground truth. And the blue shaded area are the prediction intervals generated by the corresponding systems. An interesting comparison would be, for example, the joint model and its closest competitor, which is the heteroscedastic variance. As you can see, it is the joint meta model that gets to see the inner workings of the base model that is capable of capturing effects like very harsh deviations from the actual observations in prediction. As you can see in this area where this happens, where the actual observations are further away from the prediction and the prediction error is very high, the uncertainty adaptively widens, the prediction interval widens and thus captures this uncertainty faithfully, more faithfully than the heteroscedastic variance model that seems to be missing somewhat this phenomenon. There is multiple examples in the main paper. We also provide many examples in the appendix. And for those interested, they can contact us for providing a notebook that would retrieve such images for all the test data. Just a quick recap. This paper describes a method based on the meta-modeling concept that works really nicely in sequential regression tasks, specifically for deep neural networks. We also described a novel variant of this based on joint estimation of the base and meta model and showed some nice results on 2 sequential regression tasks. We believe that the meta-modeling approach in general is a very nice addition to the toolbox of a researcher working on uncertainty quantification, and invite you to read the full paper linked here, and also encourage anyone to reach out to us with any questions. Thank you for your attention.